Yeah, let's talk about the second type of power flow method, which is called Newton-Raphson method. And so later you can tell me you like this method or the other one, the Gauss-Seidel method. Compared to Gauss-Seidel method, Newton-Raphson method is based on linear approximation. So if you want to solve a linear function, fs equals c, you simply just do a Taylor expansion on the nonlinear function, so get the value of the function at the initial guess and the linear term and second term, and you just continue. So if this function is smooth, it's differentiable at all orders. So eventually you can get it actually can converge to the value of the function. But if we ignore any terms higher than order 1, basically we only just keep a linear part, we'll have approximate formula to calculate this nonlinear function. So based on that formula, we can get the iteration. So basically the meaning of this iteration formula is just to update the value of your initial guess of x based on the gradient, which is the slope at the initial guess, and also the gap of the function value. We can generalize this formula to any order. So because any iterations, if we start from the initial guess, we call this step as step 0. We'll calculate x1. Then from x1, we'll calculate x2. So eventually, we can convert to the true value of the solution. So this formula will tell you at each iteration how much you want to update x. So it will based on the gap of the function value at that iteration, and also the gradient information at that guess. So the algorithm will be if we start from any initial guess and we set up an error tolerance, and we just utilize this formula to iterate. So if you want to visualize on how the Newton-Raphson method start from initial guess, convert to the final solution, it's actually utilize a straight line to update a small part of the curve of the function near each iteration. So if we start from initial guess, at the initial guess, we draw a tangent line. We use tangent line to approximate the curve, and we move to the next step, to x1. Then we draw another tangent line. To visualize that process, we can use example 6.4. It is the same equation to solve. So by using the Gauss-Seidel method, we can just move one x to the left, and we have iteration formula, and we just iterate, right? We plug in the initial value to the right and get the updated value on the left, and then you plug in back to the right. Then you just keep iterating until the gap or the update on the x value doesn't change much. But here we use Newton-Raphson method. So this black curve just indicates the nonlinear function of fx. C here is just 0. So this is C. So basically, just this black curve intersect with x axis. So we know from this curve, we know there's a 2 intersection point, right? The first one is a tangent point at 1.0. The second is an intersection point at 4. So the first intersection indicate 2 equal roots. The second indicate the third root. So if we start from initial guess 6, okay, so which is like we plug in the 6 into the nonlinear function, and we also we don't just utilize the value at that function, we also utilize the slope at that function. So using that slope, we can draw a straight line tangent to that point. So we use this part of the straight line to approximate that curve. So obviously it's different, but it gives you both the value of that initial guess and also the gradient information at that initial guess. So if we just illustrate how we calculate, we have this slope df by ds, which is just first order derivative with respect to x, which is a quadratic function. So if we plug in the initial gas, we'll know the slope actually here is 45. So this is 45 for the slope value. Using this slope, we draw that straight line. It will intersect with this the x-axis at this point. This is not the root. It still have certain distance to the closer root at 4, right? The distance is about 1, but we just continue. So we calculate that there's still a gap of the function which is 50. So which means this gap is 50. It's still not 0. Then we just continue. Okay. Then we update. We use the distance to update. So finally, the second iterate will start from here. That will be the S1. So we plug in the S1 into the function. We'll get a new point, and then we draw a new slope at here, right? So using this the green line to approximate that part of the nonlinear curve. After 2 iterations, we already get a value very close to the root. So you see the value is around 4.0. It's very close. So you just continue. After 5 iterations, you get a very accurate estimation of the root. Remembering using the Gauss-Seidel method, we take about 9 iterations. But here we only take 4 to 5 iterations. So Newton-Raphson method also cannot guarantee to find all roots. It can only find the root near the initial gas. So which means if the entire space can be split into some domain abstractions, and one domain is surrounding one root and another domain is surrounding another root. So there's about a boundary near 3. And on the right-hand side, if you start any iteration, it will convert to the root at 4. And on the left, it will convert to the root of 1. Depending on what this function is, but this is just a third order polynomial. But if the function is very complex, so there may be also some areas you may not convert to any to roots, so hard to convert to any roots. So if you compare the Newton-Raphson method to a Gauss-Seidel method, Gauss-Seidel method start from initial gas to draw the stairs, right? Go up and go horizontally, then go vertically, then eventually convert to a root. But this entire process doesn't utilize any grading information. Okay, so you only just draw vertical line, horizontal line, vertical line, horizontal line. But by Newton-Raphson method, each time you also go through like a zigzag iteration, but you draw the tangent line near that curve. Okay, so which you utilize grading information, give you better convergence. How do we utilize the Newton-Raphson method to n-dimensional system? So this green box just shows the procedure to solve this equation with single variable. But what if we have many variables? We have n variables to be solved, and we have n nonlinear equations. We just put those equations in the vector form. Okay, so we treat the nonlinear function as a vector valued function and variable as vectors. So we can easily generalize the Newton-Raphson method to solve this set of equations. Then the iteration formula compared to the original for one-dimensional. So we have at iteration k, we need to find the updated value. The updated value is calculated by the inverse of the slope, or the reciprocal of the slope, multiplied by the gap of the function value. So here, if we generalize this formula to an n-dimensional system, so we have a vector at k iteration, plus here is not the slope anymore, it's called Jacobian. Jacobian is a generalization of the slope from one dimension to n dimensions. So we need to calculate the inverse of the Jacobian, then multiply by the vector of that include all the gaps in each dimension for the function value. So delta S and delta C here become a vector with n dimension. Jacobian is defined in such a way it's a square matrix is n by n. So each element, like at S row and jth column, that indicate that, like for instance, S row jth column, that is actually the partial Fi, partial Xj. Fi is actually the ith nonlinear function. Xj is actually the jth variable to be solved. So you just calculate all the combinations and put them into this matrix. So this will be a Jacobian matrix. So you notice the Jacobian matrix also have this superscript parentheses with K, which means this Jacobian need to be updated. Because every step, when you have a new S value, you need to recalculate this Jacobian. So now let's use one example to show how to run the Newton-Raphson method to find the solutions for a set of equations. So we start from two equations, both are nonlinear equations. So you can find out this equation. The first equation indicates a circle centered at the origin and with a distance with radius of 2. If you treat S1 as x-axis and S2 as the y-axis, so this will be just indicate a circle of radius of 2. And the second function is some nonlinear curve. So that nonlinear curve, second nonlinear curve will intersect with the circle at 1 or 2 points, depending on the two curve, actually a tangent or it just intersect. So you can have two rules or one rules. Let's use Jacobian to run the Newton-Raphson method and to find out the rules of the two equations. So if you calculate Jacobian, Jacobian, each element will be just each nonlinear function will calculate partial derivative with respect to one variable. For instance, the first element will be the first function with respect to the first variable. So basically just partial derivative of this item with respect to S1, right? So that will be 2S1. So similarly, if we want to calculate this one, the partial F2 and partial S1. So it will be second function, we calculate the partial derivative with S1. Basically, we only have this item. So ES1. Okay, so you can do that for the other element to have a Jacobian. The Jacobian is not a constant matrix. It's actually another function valued, the matrix valued function, right? They have some elements which need to be determined, need to change with the S values. So let's give an initial guess. Although we don't know where the true solution is, let's just assume S1 equals 2, S2 equals -2. Okay, so the gap of the function will be the actual function value here is just this vector. The first element is 4, the second is 1. And we plug in the initial guess into the left-hand side of the equation, right? Then compare it to the right-hand side. So have the right-hand side vector and the left-hand side also value. So the gap is pretty large. So which means this is not the root. It's still far from the root. But don't worry, we have a Jacobian. The Jacobian will tell us how much to update this initial guess. So if we plug in those values into so we're plugging those values to the formula of Jacobian. We'll have a Jacobian with all the 4 elements determined. So next step, we just determine calculate the update. The update will be the inverse of Jacobian We need to calculate the inverse of this matrix, then multiply by the gap of the function. So we have this value. So this value indicates how much you want to update the x. So if this function is linear or pretty much linear, so this update will give you a new solution very close to the true solution. But those two functions are not linear. That will depend on how close your initial guess has been to the roots. Let's summarize the calculation in the table. So we calculate from initial guess to the first guess, and then we go to the second iteration, third iteration, until the fifth iteration. So you see the function gap start from initial guess. It will reduce, right? So eventually it will become almost zero. So Jacobian starting from our first Jacobian also updated, and the gap eventually becomes zero. So finally we have a root. Okay, this can be one of the two roots. So if you visualize what happened, that indicates the curve starting from the initial guess. We have S1 equals 2, S2 equals -2, so which actually start from here. So there's a blue circle indicate the first function, first equation, and there's another blue curve intersecting with the circle at 2 points. So those 2 points will be the two solution of the set of equation. And if we start from this point, we take about 4 to 5 iterations. So we'll get to the lower solution. Similarly, if you can try some randomly other initial guess, like say we start from here, it will may take more iteration, because that will first get to a location near the initial guess of the first one. If you try some other like initial guess, so the first step to update will go to somewhere here, and eventually it will converge to the other solution, not the first one. Okay, so what happens with the iterations of a Newton-Raphson method is it start from some initial guess, iteratively move from one point to another, right, towards the solution. By towards solution, which means it utilize the local gradient information, using the local slope of this, in which direction the function value can be updated more efficiently. The Jacobian actually gave you that information. So Jacobian will indicate the fastest direction, which is the gradient, to move from one point to the next point. Okay, starting from different initial guess, you may convert to different solution. It looks like there's a boundary in the space. So if you start at any point below that boundary, so you will convert to the lower solution. But if you start from any point above that boundary, you will convert to the other solution. On each side, there's a like domain of traction. So which means they will convert to one solution, one of the solution of the equations. Oh, okay. Any question? All right. So let's compare to Gauss-Seidel method, and then maybe you can give a more fair judgment on which one is better, which one is your favorite method. In reality, you can just keep using the same method if you're pretty clear on how to utilize all the tricks of one method. Let's think about convergence. So the Newton-Raphson method can converge much faster than Gauss-Seidel method. So we call the Newton-Raphson method as a method with quadratic convergence. By quadratic convergence, which means it's based on the linear approximation of Taylor's function. So the error is in the second order. So which means its accuracy is about second order. So we call such method as quadratic convergence. So if you want to propose another method, you use linear part and the second order part, you ignore third order, fourth order, any high order term. So you can call such method as like third order convergence. But that can give you better convergence, but that will introduce some more problem, right? More difficulty to calculate. So I will talk about that shortly. But Gauss-Seidel method doesn't utilize any differential term of the Taylor expansion. So the Gauss-Seidel method is considered only have linear convergence. Linear convergence doesn't mean it has linear approximation. It just means its error is linearly changed with the gap of the initial gas. The second aspect, we want to compare the initial gas. The Newton-Raphson method also requires an initial gas which is sufficiently close to the true solution. But here, when we say sufficiently close, so it's slightly different from Gauss-Seidel method. Gauss-Seidel method doesn't utilize any gradient information. So sometimes from an initial gas, which route we can go to has some uncertainty. But the Newton-Raphson method, you need to stay in the domain of traction. In the domain of traction, which means if you calculate local slope, that roughly point to the solution you want to go. Okay, so which is like valley. The valley, the shape of the valley may be may not be linearly changing in any direction, but if the trend is going to the center point of the solution, so you still can converge to that solution. It keep a linear term, but it still ignore the second or third or even and higher order terms. The third item, we compare the computational cost at each iteration. The Gauss-Seidel method is very simple. You just only take your effort to plug in the value to the right-hand side equation to calculate. So you only just take time for the like very fundamental operations by computer. But the Newton-Raphson method need to compute the inverse of Jacobian at every iteration. Okay, because Jacobian also need to be updated. So when you change the S value, you need to plug in the value into the Jacobian function to calculate the Jacobian value. So on this example, we see the Jacobian is not constant. So every time you update S1, S2, you need to update the Jacobian. So that's why the Jacobian is actually keep changing during this process. And every step to solve the update on the X, you need to calculate the inverse of Jacobian. So this one introduced a lot of computational effort. To summarize, the Newton-Raphson method can convert faster, but it will need more computational cost at each iteration. So it may need a few iterations, but each iteration is more expensive. How can we reduce the computational cost of Newton-Raphson method? There are some ideas. The first one is we can utilize some approximate Jacobian matrix. It doesn't have to be accurate. For instance, you can take a constant Jacobian approximation. So you keep using the same Jacobian, okay? So it's not accurate, but indicate maybe the average direction of in that domain of traction. So you just keep using that. You may have more iterations, but each time you have much lower computational cost. You don't have to solve the inverse, or at least you don't have to update the Jacobian every iteration. Maybe you need to, let's assume that we can update the Jacobian every 2 iterations or every 3 iterations. So definitely it doesn't give you the best direction to move, but it may not be too bad. Another idea is, so the difficulty of solving the inverse of a matrix can be reduced if the matrix is more like a diagonal matrix. So we know for diagonal matrix, the inverse can be calculated. Even the matrix is not fully diagonal, but we can get rid of more off-diagonal elements. We can speed up the calculation of inverse. So another idea is we can have a block diagonal approximation, which means we ignore some items in the Jacobian which are not important, okay, or small. So this directly lead to another method we'll talk about at the end of this session, which is fast decouple method. So which is one type of Newton-Raphson method, but which can be very fast. But definitely I will need maybe a few more iterations. But each iteration, the computation is very, very fast. Let's just show what happened if we use a constant Jacobian. Like go back to that single equation, Jacobian will be the slope. So we start from an initial gas 6, right? We draw this slope. So this slope is a good estimation at only the initial gas. But when we move to the new S value, ideally we want to calculate the new slope at that point. But you can tell the pink slope and the red slope, they still indicate the same direction, right? It's not like the red is positive and the pink become negative. It's still pointing to the same direction. So how about we keep using the same slope, right? We instead of drawing the pink line, we draw the red line using exactly the same slope. So just increase iteration. Eventually, it still converge to the true solution, right? So you take more iteration. So if you realize this idea in this two-dimensional system, which is like we start from initial gas, the first Jacobian will be calculated pointing to this direction. But then we calculate the inverse. So next each iteration, we keep using the same inverse. We don't update it anymore. So you take it's still moving in about the same direction. Eventually get to the final root, but definitely it will take maybe 10 to 20 iterations. But at each iteration, you don't need to solve the inverse anymore. Okay, any question?
So for Jacobian, you always find the inverse matrix.
Jacobian matrix has to be non-singular, which means for this Newton-Raphson method, that's a very good question. So first of all, the Newton-Raphson method utilizes a local gradient. Gradient means at that point, you can determine direction which is better than the other direction to update value. But what if a function is not smooth? You cannot calculate Jacobian there. Then the Newton-Raphson method fail. The Gauss method, Gauss-Seidel method doesn't fail. It doesn't utilize gradient. Gradient is something like a gradient doesn't tell. Okay, if I want to climb a mountain, if you have big picture, you see the peak is over there, right? You can go a straight line. Maybe temporarily you can just go down and then go up. The stair can be go down, go up, right? So it would be not always just climbing up, but you know where the target is. But if you don't know the target, like you're blind, you're completely blind. So you only just utilize local slope. If the slope is up, you will just go that direction, right? You can try surrounding you which direction is go up the most. You will take that direction. But from the bigger picture, this guy may move into different direction. It's just exactly like what happening here. Okay, and if you go to maybe the rod is not even. If suddenly there's a hole, you just fall into maybe there's a cleave. So which is like the function is not smooth. That slope method based method will fail, right? Initial guess will be critical. So we can assume the function near the solution is roughly smooth. Then you need to have a good initial guess to push, to actually start from a point close enough to the roots. Let's talk more about how to compute the inverse of Jacobian matrix. So why do we want to compute the Jacobian? Because we want to solve this equation for x. at each iteration, we know the function value, the true function value, and we also know the current function value. So we know the gap. That's what we want to eliminate. And we want to find the update on the S value, the variable value. And the information we can utilize only the linear part of the nonlinear function, which is Jacobian. Okay, we solve this linear equation for delta x for the next step. The straightforward method is just to calculate the inverse of Jacobian. Then we use the inverse to multiply by the gap that will give you the update. That's very straightforward. But you may think that's a very obvious, right? So let's just take this method. The problem is when you solve power flow for a power network, like for instance, 100,000 bars. Okay, 100,000 bars, which means the Jacobian will be 100,000 times 100,000. So to solve inverse of such huge matrix is very challenging. So there will be another method, which is commonly used by most of the power flow software, which is called LU decomposition. So LU decomposition is another idea. The name is a triangular factorization. So L means the lower part of the matrix, and U means upper part. So it's based on a theorem. So for any square matrix, it can be decomposed into two matrices, the product of the two matrices. And the first one is both are triangular matrices. The first one only have non-zero element on the lower part, lower triangular elements. The second only have on the upper triangular elements. So this one can be proved if it's a square matrix. So if we utilize this technique, and here we want to solve the AS equals B and for X. Okay, so definitely you can just calculate inverse of A. But instead of calculating inverse of A, you can just treat A to be equal to the product of L and U. And so the original problem solving the linear equation become solving the second equation. For the second equation, we don't need to calculate the inverse at all, because we only just need to define this product to be Y. We solve Ly equals B for Y. And the next step, we solve the US equals Y for S. And for each step, you solve the equation with all the coefficients as triangular matrix, which means you can use Gaussian elimination starting from maybe the first equation. So for the first equation, if there's only just one non-zero element, you just directly calculate that variable. Then from there, you can go to find the second. So if the matrix has a triangular form, you can directly apply Gaussian elimination. You don't need to calculate inverse at all. So this is the idea. So we can decompose the Jacobian matrix also to two triangular matrices, L and U. And when we solve the original equation for S, we just need to first solve this decomposed equation for U times delta S, right? Then second, we just solve that equation for delta S. So we don't need to compute the inverse of Jacobian. If you want to make a U program to solve linear equation or for solving power flow, if you use MATLAB to generate your code, and you have this equation to solve, you want to find out the X. And in MATLAB, you can definitely simply ways. Maybe you can just put S equals inverse. So there's a function INV J, then times Y, right? So in MATLAB, if you put that command, it will calculate the inverse of J. It will take much more time. But in MATLAB, you can use this command. You use the J \Y. So when MATLAB see this symbol, it will do the LU decomposition for you. Okay, so you can compare. You create some maybe random matrix. Make sure it's not singular, and you just run the first method and then run the second method with IU decomposition, so you can compare which one is faster. All right, so now we are ready to use Newton-Raphson method to solve power flow. We have the power flow equation. So first one and second one. So first one, we can utilize that equation to calculate for the voltage, phasors. And second, we can utilize to calculate P and Q, depending on what type of buses you want to compute. Okay, so you can pick which equation to use, but they basically indicate the same equation. For Gauss-Seidel method, we only just need to move the variable to be calculated in each iteration to the left, right? We use the right-hand side. We use either constant value or some old value, so we calculate how much where to update the variable. So if you still remember, there are two iteration formula. The first one to calculate the voltage phasor, or only just the voltage angle. The second to calculate the P and Q. Okay, depending on the bus types, so you can select the combination of those two formulas. For Newton-Raphson method, we have this equation. We don't have to split the unknown variables x into two types, one on the left, on the right, because we can move them all on the one side. So C here, it doesn't have to be, it can even be 0. But C just indicates some general nonlinear equation. So we can utilize only the second formula, which is here. So the voltage, if we consider voltage as the unknown variable to be solved, we want to linearize this equation into this form. So here is a Jacobian. The Jacobian is based on the nonlinearities of the original power flow equations. So maybe here you don't see clearly where the nonlinearity is, but when we convert the power flow equation to two real equations, so you will tell there are nonlinear function as like sine function, cosine function. So we want to linearize the equation into the Jacobian multiplied by the update on the angle and the voltage magnitude, and that will give you the update on the P and Q. All right, so now let's look into the more detailed step to form the Jacobian matrix for iteration. So we use polar form. This is our power flow equation, and we want to write two equations. The first one represents the real part, second represents nonlinear imaginary part. So first equation will tell P as a nonlinear function of, so here you see every one become absolute value. And here is a cosine theta ij. Theta ij is actually the angle difference between the buses. Delta is actually the angle of the bus, the voltage phasor, and theta ij is actually the angle of the admittance. Because we want to change the phasors, complex numbers on admittances all into the polar form. Second equation is to calculate Q. So this one will involve the sine functions. We call the two equations as equation 1 and equation 2. And we'll decide which equation to be utilized for our calculation. Okay, so our goal is to find out the Jacobian. So once we know the Jacobian, you can start iterate. The Jacobian will have this form. It will have 4 type of elements, 4 combinations. We have 2 equations about P and Q, respectively. We have 2 type variable, V and delta. So by V, I mean the absolute V. So the Jacobian will have 4 type of element like partial P, partial delta, partial P, partial V, partial Q, partial delta, and the partial Q, partial V. Let's assume we have a power network which has n buses, including bus 1 as a slab bus. So I'll always number the slab bus as bus 1 here. And we have m PV buses, so which means it could be generators, for instance. And the rest of the buses will be PQ buses. So it will be n minus 1 minus m. To form the Jacobian matrix, because from this general form, we need to calculate all the combinations. If we have n buses, we have n p's to be calculated. We also have n q's to be calculated. So it looks like the Jacobian matrix need to be 2n times 2n, right? Because like if we have a 3 bus power system, it need to be 6 by 6. You have a partial P1, partial P2, partial P3, and partial Q1, partial Q2, partial Q3. But actually, we don't have to include the slab bus because slab bus doesn't need to be solved. It needs to be calculated at the end. This is similar to the Gauss-Seidel method. So we can get rid of the slab bus. We only assume the Jacobian matrix to be starting from bus 2 until bus n. So here become 2n, 2. So dimension here will be a 2. N minus 1 times 2n minus 1, right? We just get rid of slab bus. So let's continue. Let's see what other elements can be get rid of, because the similar the Jacobian matrix is, and the easier we can do the computation at each iteration. So the Jacobian need to include m PV buses for generators. And for PV buses, we only just need to solve the angle. We already know the P and also voltage magnitude. So we need to utilize the first equation to solve those angles, because we already know those P and those values already know. Okay, we only just need to P is also known. We only just need to solve angle. So we definitely need to include elements in the Jacobian matrix about angle. That's for sure. But we don't have to include equation about Q, because once we know the voltage, absolute value, and angle, we can use the second equation to calculate Q. We don't have to utilize the Jacobian to help us to iterate, because the smaller Jacobian, the easier to calculate the inverse. So we don't need to include Q in the Jacobian. So we need to remove any raws involving partial Q related to PV buses. So for instance, if bus 2 is a PV bus, we need to cross off that raw about the partial Q. Also, because the PV bus, the voltage doesn't update, voltage magnitude doesn't update, we need to cross off that column. So if a bus 2 is a PV bus, we need to cross in the lower portion, we need to cross the first raw, and also we need to cross off one column related to V2. So which means if we have m PV buses, we need to cross off m rows and m column. So that make a Jacobian even smaller. So for the other type of buses, like PQ buses, we need to solve both voltage magnitude angle. So which means their element need to be there. So eventually, how many? What's the dimension of Jacobian matrix? So we start from 2 times n minus 1 times 2n minus 1. We also need to. This is our original dimension. So on each dimension, we have a 2n minus 1. Then then minus m, right? Right. So finally, we have this is our final dimension of Jacobian. Okay, if we draw this Jacobian, so it will look like this one. So the dimension will be 2n minus 2 minus m. So we have 4 blocks. The first block, J1, include everything except for slide bars. The J2 is not a square. It include all the rows except for slide bars, but not including the columns on slide bars and the pivot bars. So J3 is like is symmetric about the J2 in terms of the shape. It includes all columns of buses except for slide bars. But for the row, it doesn't include the slide bars and also the pivot bars. Finally, the J4 is the smallest block. It doesn't include the slide bars and the pivot bars in either row or column. Okay. All right. So on Wednesday, we'll start from here to talk about how to iterate this equation. This Wednesday is an engineering day.
They usually cancel.
Oh, okay. I will double check. Yeah.
Yeah, I just want some of the records. I get it. That's fine.